Hello students, how are you? So today we are going to start with a new topic in the chapter of excretion, and that's a very interesting topic. And I find that for some students it's a bit difficult. But before that, as always, we start our day with a very positive thought. So what's the positive thought that I've got for you today? It's a little progress each day adds up to big results. And that's so true. You just work hard, small doses of your hard work will surely give you very nice results in the end. So now, without wasting any time, let's start with the topic of glomerular filtration in the chapter of excretion. Okay, so what is the topic that we are going to do? That is glomerular filtration. Okay, we will do the process and we will do the various rates, and there, then we'll do what all things are affecting these rates and all the formulas and all. Okay, so now let's start this topic. So first I'll make a small diagram for you so that you are able to understand. Suppose this is the Bowman's capsule, and okay, now first, before making this, I'll tell you one thing, then we'll start. So first, when we start glomerular filtration, we need to know about one thing, and that is known as renal corpuscle. Because if you don't know this word, then you won't be able to understand glomerular filtration. So renal corpuscle is what? It is glomerulus and Bowman's capsule. Together is known as a renal corpuscle, right? And what is glomerulus? We already know that's a tuft of capillaries, right? That's a tuft of capillaries. Some people call glomerulus, Bowman's capsule as glomerulus capsule, right? This much is clear. Now let us see. So suppose this is the efferent arteriole, and right here is the efferent arteriole, and this is the efferent arteriole. Okay, now this is the basement membrane that I'll draw first over here, and then I'll be drawing the Bowman's capsule. Okay, I'll be drawing the Bowman's capsule over here, and these are like this, we have to draw it like this. Okay, all through. Now the interesting part comes. The interesting part is what? Interesting part is this capillaries. Why? We'll study these capillaries, and this blue colored thing that I have drawn, that's the basement membrane, I'll say in detail. Why? I'll tell you, because it's important, right? So now you can understand we have to draw like this. This is an endothelial lining. What is this? This is an endothelial lining. So this is what? This is the efferent arteriole. Okay, this is the efferent arteriole. Please understand nicely. This area in between, tuft of capillaries, is the glomerulus, and this is the Bowman's capsule. We'll do it also. This is what? This is the Bowman's capsule. and then the proximal convoluted tubule. Okay, right. Okay, so this is what we have to now study. So this, we'll do this Bowman's capsule layer afterwards. These are podocytes. We'll do these all things in detail. First, let us label all these things. So this is what? This is the parietal layer of Bowman's capsule. Please keep a notebook with you so that with me you are also drawing it, right? And these are podocytes. And what are podocytes? Podocytes are the visceral layer of Bowman's capsule. Okay. And what is this blue thing that we have drawn? This is what? This is the basement membrane. This is the basement membrane. And then from here it goes to proximal convoluted tubule. And now we'll see how all these things are functioning. So first I'll tell you something very interesting about this efferent arteriole, right? Here is what? Here is this, the glomerulus, the tuft of capillaries. Okay. Now I'll tell you something very interesting about efferent arteriole. Let us see what is that thing. So there is this point that you should know. Efferent arteriole. It is the only example in the body where a capillary bed is being fed by arteriole. Fed by arteriole means the efferent one, and being drained by arteriole. That is the efferent one. Okay. It should have been what? A venule or a vein, but it is what? It is a arteriole. That is an efferent arteriole. So this is a good example where the only capillary bed which is being drained by an arteriole and fed by an arteriole, right? Now, so this, you can see that I have made these in these capillaries, in this endothelial lining, right? This endothelial lining, there are small pores. So now we'll see this endothelial lining in a bit of detail so that we can understand the process of this glomerular filtration, because this is a very important thing. So let us now see this thing in detail. Okay, so suppose this is one what? Endothelial cell, right? Suppose this is one endothelial cell. Now see what I'm going to draw. There are thousands of these, right? Hundreds and hundreds and thousands of these. And what are these holes? These holes are what? These holes are the fenestrations. Okay, these holes are what? These are fenestrations. And what is the size of these fenestrations? Very small. These guys are very small, 50 to 100 nanometer in diameter. Okay, right? 50 to 100 nanometer in diameter. So what can actually pass through this? This is endothelial cells with small holes or fenestrations. Why are these fenestrations? If there are holes, something will pass through it. So we'll see what can actually filter through this. Any idea what can actually filter through this? Blood that's coming. Blood is made up of what? plasma that has a lot of water in it and formed elements, right? And formed elements. And what are the formed elements? Do you remember? Like RBC, WBCs, and what? Platelets. So any formed element, any type of formed element cannot fit through these fenestrations. Why I have made this cross? Because any type of formed element, any type of formed like RBC, WBC or platelets cannot fit through these fenestrations. Chalo, एक बात तो हो गई. These formed elements cannot go. Now what can go? What cannot go तो हो गया. What cannot go? What can go now? The question comes, what can pass? What can pass? Now let us see. Small to moderate proteins, small to moderate size proteins, water. What are these? These are different components of plasma, right? Because we have already seen that form elements cannot go, so plasma is left. Water, electrolytes, waste products, nutrients, these all can pass through this fenestrated endothelial lining. Okay, this much is clear to us. Now let us see what comes after this endothelial lining. There comes this basement membrane. Now let us see something about basement membrane and why it is very important. Basement membrane is very important. Now let us see something about this also, right? So basement membrane, first of all, we have to understand that this basement membrane is a very important or a very critical part of glomerulus. Now why? The question comes, why? Why is it important? And that we will answer now. Suppose this is a basement membrane, right? What is this? This is a basement membrane. It is made up of 3 parts. Now let's see properly. It is made up of 3 parts, and in between there is a very thick and a dense part. What is this? It's not needed, but then I'm just telling you, don't need to remember this name. This is lamina densa. And why it is lamina densa? It is made up of, it is a very, first of all, it is a very thick layer. And what is it made up of? It is made up of type 4 collagen and the protein that is known as laminase, and it is very dense. It is very dense, right? And these parts, it is made up of 3 parts, 1, 2, 3, 1, 2, and 3. So these 2, 1 and the third part are made up of few glycoproteins. Okay, and what are we talking about? We are talking about the basement membrane, right? And this side is the endothelial side, right? This side is the endothelial side, and this side is the podocyte side. Okay, this side is what? This is the, okay, this is the podocyte side. So this is made up of glycoprotein. Now we know that if it is a glycoprotein, what will be the charges? This basement membrane will be what? It will be negatively charged. Now this negatively charged is very, very important, right? This negatively charged is very, very important. Why? Because if this is a basement membrane and this is this collagen and this is negatively charged, what will happen if some kind of protein such as albumin, suppose here comes a protein called albumin. This is what? This is albumin. This is what? This will also be negatively charged. What will happen when it will come? What will happen when it will try to pass through this basement membrane? It will be repelled. It will be repelled. So there are various plasma proteins. Suppose there is fibrinogen. Suppose this is what? This is also negatively charged. This what I have drawn, this is fibrinogen. What will happen when it will try to pass? It will be repelled. Then what will come inside? Obviously, what will come inside? Something that is positively charged. That will what will happen to these positively charged particles? They will be able to easily pass through this basement membrane. Now let us see in our diagram what is actually happening. Suppose I told you what, there is some kind of a plasma protein. Suppose this is albumin. What will happen when it tries to come over here? This basement membrane is negatively charged, right? Now we know this is negatively charged. It tries to come. It is repelled. Now again, if suppose there is this fibrinogen, this is negatively charged. It tries to come. It is repelled. Now what will come? That is positively charged. Suppose some electrolytes, sodium, potassium, magnesium, calcium, right? Few glucose, amino acids, nutrients. Remember I said nutrients will pass through it, waste products will pass through it, creatinine, water. These are all parts of plasma. Bicarbonates, although negatively charged, but since electrolyte, it will pass, but with less, that will more difficulty as compared to the positive. So what will happen to this? This will pass over here. They all will pass from here to this. Water will also pass, right? This water will also come, right? So we have seen, but there are other things also to see. We have just seen the size of these fenestrations, or in this which we have the fenestrations, they were 50 to 100 nanometers, right? Then we saw the basement membrane, the negatively charged. But then there are also other things also. What are those other things? Then we have those podocytes. Now let us come to these podocytes. In these podocytes also, there are two things. First is this space that we see, that we can see this space, right? What is this space? This space is the filtration slit. This space is the filtration slit, and it is 25 to 30 nanometer in diameter, and it is of very great importance. So remember this 25 to 30 nanometer. Then there are specific proteins which are like clinged together like this, and these proteins are present in between all the podocytes, and these proteins are known as nephrins, and they allow particles of only 7 to 9 nanometer in diameter, right? So now let us just draw these podocytes also and see what is happening. Suppose these are two podocytes. Podocytes means, podo means feet, and these have these kind of things, feet-like structure. That's why they are known as podocytes. And what is the space? What is this space? This is a filtration slit. Between two podocytes, this is a filtration slit, which is allowing what? Which is allowing particles or molecules of only 25 to 30 nanometer in size. And then we have those nephrins proteins. These are nephrins protein, and these nephrin proteins are allowing only 7 to 9 nanometer in diameter molecules, right? Please remember this. These nephrin proteins are also known as slit diaphragms. Okay, please remember this. And these are what? These are podocytes. Okay. Okay, so this all we have understood now. Now what will happen? Now let us see what will happen if some macromolecule comes, right? If some macromolecules come. We have seen that what all can pass and what all cannot pass, right? Now suppose a macromolecule comes. Now suppose a macromolecule gets through this basement membrane. Somehow it just passes through the basement membrane and then through slit also, and then through that slit also, and reaches the nephrins. So basically what is happening? Basically what is happening that suppose these were the endothelial fenestrated cells, right? And there was this basement membrane, right? There was this basement membrane, and then there were these podocytes, remember? Okay, so what happened? A macromolecule came and somehow it passed, which was very big in size, but somehow it just passed through it and reached through this, and it passed through the slit also, and then it passed through, and then it reached where? Then it reached to these nephrins. What will happen to this particle? Because it is a macromolecule, what will happen? This is allowing how much? Anything which is bigger than 7 to 9 nanometer in diameter, it will not allow to pass through, right? So what will happen to this particle? This particle will be hanging like a monkey. This particle will be hanging like a monkey. Now what will happen? Now what will happen to this molecule? Now one very important, what will happen? Some Pacmans will come to eat it. You know, what will happen? Some Pacmans will come to eat it. And what are these Pacmans called? These Pacmans are known as the mesangial cells. These are known as the mesangial cells. Now let me draw here these. Here we have these Pacman. You can see the many cells. I'm drawing them as Pacmans. Why am I drawing this as Pacman? I'll tell you. Why? Because these are what? These I'm drawing. These are all mesangial cells. And why I am drawing them like Pacmans? Because they are phagocytic cells. These are phagocytic cells. Any macromolecule that comes, they will engulf it. They will do what? They will engulf it, right? So now we have understood what all particles are going, what all molecules are not going, and if some macromolecule comes, what will happen. So just let us revise quickly. We started that we'll today study glomerular filtration, the process and the rates. So now we'll do the rates. Then we said before starting we should understand what is a renal corpuscle. What is a renal corpuscle? Renal corpuscle is what? Glomerulus plus Bowman's capsule. And glomerular is nothing, just a tuft of capillaries. Then we understood that glomerulus is what? It is endothelial lining, that we saw that it is fenestrated, and glomerular basement membrane, which is negatively charged and is not allowing the plasma proteins to pass through it, but it is allowing electrolytes, nutrients, waste products, urea, all these things it is allowing to pass through it. and it is acting like a very good filter. Then we saw that these fenestrations are allowing how much? 50 to 100 nanometer in diameter particles. Then we saw that there is this basement membrane, and then this slit is allowing how much? This slit is allowing particles of 25 to 30 nanometer in diameter. And then there is this protein nephrin, which is allowing how much? 7 to 9 nanometer in diameter particles. And somehow if a very big macromolecule comes, what happens? These mesangial cells come as phagocytes and engulf those particles. Now we studied all these things, right? Now we have to do the various pressures associated. Now what we'll do the various pressures, and what we'll do the net filtration. We'll do now the net filtration pressure, and the glomerular filtration rate, right? So what is this glomerular filtration rate that we are going to do? It is, let us write something about glomerular filtration rate. It is some rate, so it will happen in some particular time, some amount in some particular time. So amount of filtrate formed in all renal corpuscles. Now you know what are renal corpuscles? Of how many kidneys? Of both kidneys. In how much time? In each minute. Means in 1 minute, the amount of filtrate that is formed. And the value is 125 milliliter per minute. How we reached to this? I will tell you. How we reached to this 125 milliliter per minute. So in 1 minute, what happens? 1200 milliliter of blood is passing from where? From the efferent arteriole. From where? From the efferent arteriole, right? But only 625 milliliter is being used in filtration process, right? Only 625 is being used in the, so suppose what I'm trying to say, that this is the efferent arteriole and this is the efferent arteriole, and here we have this Bowman's capsule with the basement membrane and all. So what is actually happening? What is actually happening? That 1200 is passing through, right? So 1200 is passing through. Suppose this is this, and there we have this fenestrated, and then this, and then this, right? So what is actually happening? 1200 is coming. 1200 is coming, 1200 milliliter per minute we are talking about, but only 625 is used in the filtration process. And how much is left? That goes to the efferent arteriole. The remaining, the 575, 625 milliliter is per minute we are talking about. Remember this, we are talking about, because we are talking of some rate. So what happens? 1200 milliliter came, 625 went for filtration, and 575 is passed out. So how much is passed out? 575 milliliter is passing out. Understood? Not very difficult to understand, simple calculations. Now see this 625 that is getting filtered. Out of this 625 milliliter per minute, only 20% is going to be filtered, right? And what is 20% of 625? That's 125 milliliter per minute. And that's the amount of filtrate formed in renal corpuscles. That is the amount of filtrate formed in renal corpuscle of both kidneys in 1 minute. And this is what? This is the glomerular filtration rate. Okay, now understood how we got this? How we got this 125 milliliter per minute. Very easy to understand, nothing very difficult, right? Now let us study about the various pressures that are associated with this, right? So now let us do the factors affecting, I'll write GFR, glomerular filtration rate, right? So the first thing that we are going to do is the net filtration pressure. Now, bhai, what is this net filtration pressure? Whenever there is something net, there is something in and out, less and more, debit and credit type of thing. So this is what? This is the pressure forcing out something, few things, minus pressure pulling things in. Now let us see what are we trying to say when we saying pressure forcing out and pressure pulling things in. Now let us see, right? So here we will study about few things, few terms. Those terms will be what? Those terms will be glomerular hydrostatic pressure, colloid osmotic pressure, and capsular hydrostatic pressure. Now let us study all these three pressures and then we'll arrive at the net filtration pressure. Chalo bhai. So the first thing that I wrote was glomerular hydrostatic pressure. Glomerular hydrostatic pressure, right? What is this? What is this? It is the pressure that is actually trying to push the things or the plasma component out of the fenestrated capillary. What I am saying? What am I saying? Right. Suppose this is the efferent. I'll change the color. Suppose this is the efferent arteriole, right? This is the efferent arteriole. And here we have what? Here we have this Bowman's capsule. And right here we have everything. And this is the capillary that I am talking about, right? Okay, so this is the efferent arteriole and this is the efferent arteriole. Now we have to study. So this is the pressure that is actually trying to push things out of the fenestrated capillary. Understood? Now got it? It is the pressure. It is actually, it is what? It is actually what? The glomerular hydrostatic pressure. It is actually trying to push plasma components, remember water, electrolytes, out of the fenestrated capillary. And on an average, it is about 55 millimeters of mercury, right? Now, let us see the other thing, that is COP, colloid osmotic pressure. Colloid osmotic pressure. Let us write the full form. Colloid osmotic pressure. Now, what is this colloid osmotic pressure? It is exerted by the plasma protein that are trying to keep the water in the blood. Matlab, it is exerted by the plasma protein, okay, this side pressure, as opposed to the hydrostatic pressure that is exerted by the plasma protein that are trying to retain the water in the blood, right? There are plasma protein that are trying to retain the water in the blood. So it is the pressure exerted by those plasma proteins. So what is this? It is opposed to glomerular hydrostatic pressure. And what is this? It is exerted by plasma proteins that are trying to keep water in the blood, right? And actually this is on an average 33 millimeters of mercury. Okay. Now, one more thing we had written. What was that thing? Let us see. We had written something called CHP. That's the capsular hydrostatic pressure. Capsular hydrostatic pressure. And what is this actually? This is the back pressure, or we can also call as it is trying to push back. What is trying to push back? Suppose this is the Bowman's capsule and some things are coming, something is getting filtered, and suppose there is this funnel that is trying to filter things, right? So when we are just putting things inside, a point will be reached. We will reach a point when this will get filled. Suppose we are trying to fill something in the funnel and we are putting a lot of pressure. What will happen? This will get filled. So this will also exert a pressure back, right? This will also exert a pressure back. And this pressure is the capsular hydrostatic pressure. Don't get confused with these arrows, right? This pressure is the capsular hydrostatic pressure. So which pressure? Suppose this is the funnel, right? So it is getting filled, being overloaded. So this pressure is the capsular hydrostatic pressure, right? So now let us see. Now, so what will be the net filtration pressure? It will be what? We saw that there is this glomerular hydrostatic pressure. Then we saw there is this colloid osmotic pressure. And then we saw there is this capsular hydrostatic pressure, right? So what will be the net filtration pressure? It will be very easy, right? And 55, and it is what? It is 10 on an average. It is 10 millimeters of mercury. So net filtration pressure is approximately 10 millimeters of mercury, right? And we got it how, right? So now we can say that this net filtration pressure is directly proportional to the glomerular filtration rate that we have already done, right? So in other words, what we can say, that if it increases, the glomerular filtration rate will increase, and if this pressure decreases, this glomerular filtration rate will decrease. So we have done one factor that is affecting the glomerular filtration rate, right? That was the one factor that's affecting glomerular filtration rate. Now let us see the other. Now let us see some other factors that affect. What is the other factor that affect? So we'll study two things in it. First, we'll study the surface area of, in the second point, we'll study two things that are affecting the GFR or the glomerular filtration rate. The surface area and the permeability, the porousness, how porous it is, right? Now let us see what is this. Suppose this is the efferent arteriole, right? This is the efferent arteriole and this is this Bowman's capsule, right? And similarly, suppose this is this. What have I done? Everything similar. Everything is similar, but what have I done? I have just increased the surface area, right? I have just increased here we have this small surface area of glomerulus. Here we have large surface area, right? So what will happen? It's just common sense. The smaller the surface area, the lower the glomerular filtration rate. The larger the surface area, the greater the. So one more thing we have understood. Now the permeability. Suppose this is this efferent arteriole, everything keeping same. The surface area I am keeping now same in both. Please remember the surface area is same, right? Now surface area is same, but there are only suppose 3 fenestrations and here I have many fenestrations. What will happen? Obviously what will happen? Here we have what? Here we'll have lower. Obviously, because the rate will be less. No, because there are less fenestrations, and here will be higher rate. Very easy to understand. So, suppose one clinical example I'll give you, that if you want, just for your interest, once there is this disease called glomerular nephritis. In that, what happens? Basically what happens is that it destroys the basement membrane, and when it destroys the basement membrane, basically what happens, there is a very higher rate of filtration, and then what is the net result? The net result is that we lose a lot of protein. This is just for your interest that I am telling you, right? So now we can say that the surface area of glomerulus and the permeability of glomerulus, they are known as, by one more, these two both things are known as KF together, or the filtration or the filtration coefficient. And what is this filtration coefficient? These two things together. So now we have arrived at a very wonderful formula that I was trying to write since so long. Glomerular filtration rate is equal to net filtration pressure into the filtration coefficient. Glomerular filtration. I just want to write because we did all these things just to reach here. Net. So we have done the process. We have done net filtration pressure, GFR, and the filtration coefficient. We have understood everything, not leaving anything that is important. Okay, this we had to arrive here. That was our goal, and for that we studied everything: glomerular filtration, the process and the rates and the pressures. Now just a few things I'll tell you, and one very small thing, and then we'll end. And that thing is what could be the certain situation that can affect these things, right? That can affect these pressures that we have talked about, right? So the thing that we are not going to do is, what the question that I'm going to solve is, what could be certain situations, what could be certain situations that can affect these pressures we have talked about. These pressures, what pressures? These pressures, right? Capsular hydrostatic pressure, right? So this is directly dependent. First thing we are doing, first thing, it is directly dependent on blood pressure or systemic blood pressure. So if the blood pressure is high, glomerular hydrostatic pressure is high, and if this is low, this is also low, right? Now let us do the other thing. Colloid osmotic pressure, it is how to say it, if the proteins are high, if you're holding a lot of proteins, this pressure becomes high. Why? Because like in a condition called multiple myeloma, what happens, you hold a lot of proteins, and when you hold a lot of proteins, what happens, you hold a lot of water, and when you hold a lot of water, this pressure will increase. And if there is a condition called hypoprotein, when this will decrease because you are losing lot of water. Okay, loss of water, so this will decrease. And then this third thing, capsular hydrostatic pressure. Suppose there is a kidney stone. Yeah, this will be a good example. Suppose there is a kidney stone of big kidney stone of 5 millimeter in diameter, and it is stuck. There is a kidney stone and it is stuck in the loop, in the nephron loop. It is stuck in the loop, right? So this is like this. This is, so suppose this kidney stone is stuck. What will happen? It will obviously exert a pressure. It will obviously exert a pressure, and this will also increase, right? So this is right. This is all for today, and this is a very important topic that we have done today. And so we did today glomerular filtration, and this is a very, very important topic in excretion. In fact, most of the questions are asked from this topic, right? Most of the questions are asked from this topic. So kindly see this again and again and make notes and then study. Okay guys, stay safe. Bye.